So what we're going to start with is somewhere in here, I think. Yeah. So we're going to start with this. Talked about preparing a solution. And on this one, you didn't have to figure out the strength or anything. So the official, oh Lord have mercy, I don't know mine. All right. All right, so I've watched a couple of videos of this for different people, but it has not, like the official AP answer has not come out on this one. So we can kind of talk about a couple of different things. I had one that there wasn't really that many steps in it. And then the other one that there was a lot more steps. So it tells you that you're using weigh paper to measure the determined mass of solid silver nitrate. So you don't have to use all of these different things. Like you should recognize that you're going to need a volumetric flask. Try to fit that in there somewhere. Neither one of the ones I saw talked anything about putting protective eyewear on, but you might want to list that. I don't think they would take off for it, obviously. So you've already got the silver nitrate on a little piece of weight paper. So the next thing that you do is that you would need to put that silver nitrate into which one of these? Making a 200, we're making, if you read above, we need 200 mils of a silver nitrate solution. And number one says we've already measured it out. So what would be our next step? Where does that silver nitrate go? Not into the beaker. What would it go into instead that we talked about yesterday? The flask, the volumetric flask. It's going to do a lot of abbreviating. Don't do that on the real AP test. One of them I saw where they said they would rinse the weigh paper with some distilled water into the volumetric flask. So in case there was any little granules, the other one didn't. I think that that's a good step to put. It's paper with distilled water into the volumetric flask. That gets if there's any little crystals. Now remember, we don't fill it all the way up to begin with, because now I've got my silver nitrate in the volumetric flask. So our next step, does anybody remember what we would do with that? Before we do that, we got to put a little bit of water in it. So remember, we don't want to put it all the way up to the 200 fill line. So put distilled water into volumetric flask to about, I don't know, you could say probably about 150 mLs. Doesn't have to be exact. You just don't want to say that you filled it all the way up to the top. So we said after we did that, and we had our solid in there and it wasn't all the way filled to the top, what did we do next? To dissolve that part of it. Remember we swirled. Swirl the flask until dissolved. So now we got it all dissolved. So now we would need to fill up to the 200 mark. water. And you might want to say something about using the pipette. At the end. Because if you have water, like let's say that we put water in our graduated cylinder just to pour, if you're trying to pour out of that, there's a lot more chance that you're going to go over than if you got too close, you could use your pipette. One of those mentioned it and one of them did not mention it. So like I said, we'll look again whenever they actually finally release this one. So we're there, and then now is when we would cap a volumetric flask and avert at least, for some reason, 10 is a magic. About 10 times. So kind of the big picture out of that is that I think that to get any kind of credit, you need to definitely use that. Like if you said you were mixing all this in just a 250 ml beaker, you know, that's not going to give you any credit. You need it to say that. The other thing that you really needed to know was that you don't automatically fill it to 200 right away. That would be another big point in it. And then, like I said, depending on how much time you have, you might want to throw in some other things, like make sure you put your goggles on, even though this is, if that was an acid or a base that you're mixing, you 100% need to say that you need to put your protective wear on there. This one, silver nitrate, I mean, it's not very caustic. So, but I still would include it if I had time. All right, y'all got any questions on that one? All right. Leave that there. Now, the next one is one of the diagrams that you see. And I know we haven't covered a lot of this, but if you look above at D, at that reaction, that's just a net reaction, net ionic reaction of a redox reaction. So it is something that we have dealt with. You know, get on this one. I'm just because I can't, it's not in view here, and it does become important. AL. So we have some solid aluminum. That's what that is right there. If it's solid, you just either see it on the bottom or on the side. The solid should not be floating around because obviously it's too heavy. All the little ions, because this is a water solution, all the little ions should be floating around. So that's how you would have to make sure. So at this point, you have to look and say, all right, I started with 4 aluminum ions. I'm sorry, aluminum metal. I ended up with only 2. So that means for my aluminum, I went, I'm trying to think how to do this. So with my, let me just rewrite because I do really need, sorry, y'all, I'm trying to think the best way to do this. Let me see if I can get this rewritten here. Very tiny. Are you trying to get it written? All right, so we would use something that's called a rice table in here. We use it a lot. And a rice would be an easy way to look at this. Rice, R stands for your reaction. If you want to jot that down. I stands for initial. C stands for change. And E stands for equilibrium. And the reason it becomes important because it helps you keep up with the mole to mole ratio. So this would be my R. I need to find out my initial, my C, and then my equilibrium. What we do know is that we have two aluminum ions at equilibrium. That's kind of the taking off point that becomes very important. we started off with four ions. So that means there was a difference of 2. The change was 2. If we count up our silver ions, we started with 8. Notice that this is a 1-to-3 ratio. So if I use 2 of the aluminum atoms, how many of the silver ions would I have to use to go with it? 6, exactly. So I had to use 6 of those. So that gives me at the end, that gives me 2. So far, I know I have 2 aluminum, which are already written. I'm going to have 2. This is my silver ion. And then whenever we get over here to the other side, my aluminum ion now, it's still on a 1-to-1. So that means when I reach equilibrium, if I use 2, I have to have 2 of the aluminum ions left. This is what starts the whole problem. You have to then relate it. All right, so how many pieces of silver metal should I have left? At the end, how many? Because because look again, aluminum is a 1-to-3 ratio. So if I used 2 pieces of aluminum metal, how many pieces of silver ion, or how much silver ion is that going to cause to release? 6, right? 6, okay? And once again, this has to do all with the mole ratio, which is going to be your coefficients. If I have 2, that means 2 of my aluminum reacted. So for every 2 aluminum that react, for every 1 aluminum that reacts, I get 3 silver ions, but we said 2. So that's where I get my 6 from. So this is just going to be silver. So that's what I have. My aluminum's already written in here. My next thing is silver. And at this point, this is a silver atom. It's no longer an ion. So you need to make those kind of along the bottom here. My drawing is horrible. All of those are silver. And once again, because that's a metal, you have to put it on the bottom, like, because it would precipitate. You would actually see some silver looking particles. Now, the other 2 things that I have left are ions. So I do want them floating around in solution. And I'm going to try to use this size that they've given me. So I have 2 aluminum, and they're kind of smaller. Those are my 2 aluminum, and you do need to put your charge on it. I just don't have room. And then a little bit bigger is going to be my silver ions. And when I get through, I said I have 2 of those left. So I'm going to make those a little bit bigger. I can draw better than me. So the takeaway here, and I'm just trying to introduce these more through the year and not wait to the end. So kind of the takeaway here is that connecting to moles by looking at the coefficients and using mole to mole ratio is going to be a big deal the whole time that we do chemistry, the whole year. Also, the thing that could have gotten you here, if you had those silver atoms floating around, you wouldn't have gotten credit for it. So remember, when they don't have a charge, that's just an aluminum neutral atom. Once they have a charge, that means they have lost or gained electrons. All right, look here. I have 2 positive ions, so they're both metals. But the silver is a little bit larger than the aluminum. Anybody have any idea why it would be a little bit larger than the aluminum? How many electrons has this? Yes, lost more electrons, right? The silver has only lost 1 electron. The aluminum has lost 3. So it's lost more electrons, and we'll be doing this later, but do y'all remember ZEF, ZEF from periodic table trends, where the electrons can be pulled in Now it's easier to pull those remaining electrons in toward the nucleus, and it ends up being smaller. So that just kind of gives you an idea of how the FRQs, like when you see them on the test, it's not going to just cover one thing. They like to put multiple different things together. All right, any questions on that? And when they finally eventually release that, we'll go back and look at the official terminology they like. All righty, I think we were. All right, we were talking about types of reactions. We did all of this. So tomorrow is just going to be a quiz with some formulas and working through the problems. I'm not going to ask you anything about types of reactions or anything about making that, making a solution. Right. So we're going to go through our types of reactions. Of course, we get more in depth than we did in Chem 1, especially with our double replacement reactions. Those are kind of the ones that become a pain. All right, so kind of to start off with, if we look at under types of reactions, first of all, it says the somatics. I don't have this isn't in this set of notes for some reason. Remember, a chemical equation represents a chemical reaction. So if you're talking about the actual reaction, that's not from the equation. It's just representing it. And especially the part that's important, like I said, is the coefficients for the mole to mole ratio. You're really going to have to use your phase symbols. We didn't do that so much in Chem 1. So solid, liquid, gas, and AQ is always a water solution. The types of reactions that we're working with right now do not show energy or time. Toward the end of the year, we'll get to thermochemical reactions, and then those having a number that shows whether it's endothermic or exothermic. Okay. All right. Is our composition reaction. So something is being made. Two or more simpler substances come together to form one product. Remember, those are always going to have just one product. So they yield just a single product. So an example of that would be if I have magnesium, that would be a piece of metal, nitrogen, diatomic, and it comes together to form magnesium nitride. Hydrogen plus oxygen giving me water. That's an example also. Synthesis reaction. We don't really do a whole lot of those. So that is going to be your decomposition reactions where you break something down. So kind of think of them as being, kind of think of the synthesis and the decomposition as kind of being connected to each other. But if you've memorized the different types of decomposition reactions, where that's probably the one that you have to memorize the most memorization, then if you just reverse it, then you're going to have, then you would be able to look at it as a synthesis reaction. Remember, in a decomposition reaction, it's just the opposite. So now we start with just one reactant and we end up with two or more products. Doesn't just have to be two. A lot of times it is just two. So H2O2 is hydrogen peroxide. And it says, why do we store it in a brown bottle? Anybody know? What's happening to this hydrogen peroxide? Yeah, decomposing, right? And what's causing it to decompose is some energy. Because most decomposition reactions need energy. But that is a big E. So in a brown bottle, then the energy that would get to it would be some type of light energy. And then it would break down to just water and oxygen. So when you poured it on and you want that bubbling because you think it's doing a lot of good, then you wouldn't end up having any bubbling because it would have already broken down. Actions, we kind of do a little bit with these. All right, remember single replacement reactions, we have a compound and a single element, and that single element is trying to replace something in the compound. Remember metals, and I don't know if you remember, but hydrogen, even though it's not a metal, it was on that side of the activity series. So metals replace metals, and non-metals replace non-metals. So in other words, if I look at this one, I have zinc and hydrochloric acid. That zinc, because it's it's a positive ion when it loses electrons. The zinc is trying to kick out the hydrogen. It would not try to kick out the chloride. Now, whenever you were in Chem 1, you had the trusty, handy activity series, but of course you don't get that anymore. They don't give you that. So let's talk about reactivity a little bit. I will say this, that usually AP, my test and AP test, I think they're usually pretty good about asking kind of showing you the kind of the big picture, not really getting down to the little tiny details. So remember with metals, group 1 is the most reactive. And reactivity increases down a group. So in other words, if I had lithium and it was trying to replace the sodium and sodium chloride, I should be able to look at that and say, well, that's not going to happen because lithium isn't as reactive. So that means francium is the most reactive metal on the whole periodic table for several different reasons. So now if we look at our non-metals, which group is the most reactive of our non-metals? Group 17. Group 17, most reactive. And with them, reactivity increases up a group. So that means fluorine is your most reactive non-metal. Remember, we'll talk as we get to periodic trends, we'll talk about a lot of different trends. A lot of times the noble gases are kind of left off the trend because they're so very non-reactive. Single replacement reactions are carried out in an aqueous solution. Because for a single replacement to work, I have to have an ion formed so the metals could, or a non-metal can exchange places. So I have to have it in aqueous. Right, any questions on that? All right, then we'll go to the double replacement reactions, which definitely make up the majority of what you'll see what we work with. So double replacement reactions, they're sometimes also called precipitation. Reactions. They're always also in an aqueous solution. Once again, those ions have to be formed so they can react. Precipitation is a little bit of a, I don't know, kind of not totally true, because there's other ways that you can have double replacement reactions except without it being a precipitate. So remember that if you look at your picture, remember what we're talking about. If we mix two solutions together that are clear, they could be blue, they could be yellow, that doesn't matter, but they're clear, and I mix them together and then I end up forming a solid, that's what the precipitate is. That's what we're talking about. So this is the area where we have to have our solubility rules. also not on any kind of reference sheet on AP Chemistry. So in general form, remember that, like if we're looking, I know this got separated, so it's not very good to see. So here we have our metals are trying to exchange places. We do not need a activity series, but what we do need to look at is the solubility rules whenever we get to our products. So for example, I have lead nitrate and potassium iodide in aqueous solution. So when we're at this point, everything is ions. They're all floating around as ions. When I mix them together, the lead and the iodide are going to find each other. They're more attracted to each other than to the water. So they come together and they form the solid. That would be my precipitate. The potassium nitrate, you wouldn't see anything about it because they're all ions still floating around. So remember, if you had two AQs, then that's going to equal a no reaction. So what that means is everything stays as ions. Everything is more attracted to the water, or the more water's more attracted to it than each other. So that's why they stay in solutions. And I think that's kind of what the next little blurb says, just because it's a double replacement reaction. So some other things that besides AQ that you may see water formed. That is a neutralization reaction. Acid plus a base. So if I see that water's formed, if that's one of the products, then that's going to be a good reaction. And we did that in Chem 1. What we did not do was another thing that you can look at is a gas would be formed. That also tells you that it's a good reaction. So we divide them into water, into gas, but really all of them are some type of molecular compound. If some type of molecular compound is formed, then that can also be a good reaction. So you can also look at that. Just because an acid and a base are mixed together doesn't mean it's going to be neutral at a pH of 7. So that's a little bit of a misnomer also, and we'll find out that second semester. But if I'm doing like a strong acid and base, so like hydrochloric acid and some sodium hydroxide, that would be 7 whenever it got to its equivalence point. So the other place that you're going to see some of the gases are on this little handy dandy chart. It is nice to have around. All right, I guess I can't make that any bigger. So if you'll look at it, it's going to be right in this section. So if those compounds are formed, H2CO3, H2SO3, or the HNO2, if they're formed, they're not stable, they immediately break down into these gases. Same thing with ammonium hydroxide. And I wrote that also down here because I didn't have room to stick the G's in there. So you should never have this as a product. If that's formed as a product, you need to immediately write it as this. So if those gases are formed, then that's going to be a sign that it's also a good reaction. And it talks about all of them right here under driving forces. Precipitate, that's our normal one. Weak electrolyte, so that'd be water or weak acid or a gas formation. These two, hydrosulfuric acid and cyanic acid, those exist as gases at room temperature. So that's why they're under there. So this becomes pretty handy until you kind of start getting used to it. Also notice that this has some solubility rules too that are pretty pared down because you can get hold of some really long solubility rules. Right, then we're coming to the good old combustion reaction. So a combustion reaction involves a reaction between some substance that's combustible and an oxidizer. Remember, an oxidizer is just another name for an oxidizing agent. If it's an oxidizing agent, that means it was reduced in the reaction, so that means it gained electrons. So the products of these reactions are simply oxides of what is combusted. We only did really one type whenever we looked at Chem 1, and we looked at what's going on right here, your hydrocarbons. Remember, we had any kind of hydrocarbon, we combusted it in the presence of oxygen, and you would end up with H2O plus CO2. But that's not the only kind of combustion reaction. There's other kinds, and you can see right down here. I'll move the page in a minute, but right down there, it's showing you also magnesium plus oxygen gives me, that cannot be correct. Is that a correct reaction? That carbon come from, I think that this has to be a typo. So it would give me magnesium oxide. Oh, I guess they're saying that would be silly to write that answer. Okay, let me move it up some. Now I'm gonna read it better. So what it's saying on these notes, I didn't read it good. If this, we typically think it's always going to form CO2 and H2O, but then it means. So this is going to be your good reaction. Think about the hydrocarbons with oxygen. Those release a lot of energy. They are very exothermic. So that's why we use hydrocarbons for different types of fuel. If you read at the top, this little paragraph right up here, it's not it, I don't have it on my notes, but what it's talking about is glucose. So glucose is a hydrocarbon, and it's broken down. It does release a lot of energy, but because of enzymes in the body, it's controlled. If it wasn't controlled, then it could be dangerous for that to happen in our body. Compared to most of the other hydrocarbons that we have, they release a lot of energy all at once, which we use for fuel. So that's kind of just what that little part blurb went to up there. All right, so here are some solubility rules. So a couple of things that you need to know. Nitrates are always soluble. Group 1 metals are always soluble. Ammonium compounds, those are all soluble. Chloride, bromide, iodide, they're soluble except when they're combined with these heavy guys. And the way that you'll see these are not my notes. I got them from somebody else. I've used them, but there's a lot of mnemonics in there. I don't know if you like mnemonics. What I do to help me memorize that, I think we're doing you have to write your little, so AP, we're taking AP, and then I put the H on the bottom. To me, that looks like AP chemistry as hell. So I'm sure you remember it. These are heavy, and those will be the exceptions a lot of times. Hydroxide salts, we talked about that earlier. Group 1 combined with a hydroxide, those are always going to be soluble. Group 2 pretty much, except we have a couple of exceptions that are at the top of group 2 that sometimes are not soluble. And then the other ones, it lists you a bunch of ions that are slightly soluble. So if you look in your notes, Big Mama, Big Daddy, halides, those are kind of some mnemonics that might help you memorize it. Because that is something you're going to have to memorize. Oh, I need to add something. Let's see. Formation of a gas, we kind of already jumped ahead and talked about that. So gases may form Is that on y'all's other side? I think I've already talked about most of this, and they're listed on that green sheet. So gases may form from a double replacement reaction. Like I said, that would be a driving force. These are the ones that I already showed you that would not exist like that as a product. They're going to immediately break down. So if you produced H2CO3, you could write it, but then you would need to show that it immediately breaks down into water and CO2 gas. Same thing for those others that were on that sheet. H2SO3, that's going to immediately break down to water and sulfur dioxide gas. All right. Let's see what here. And this one is showing you the ammonium hydroxide one. That's what this example. So if I produce ammonium hydroxide, not stable, doesn't exist, it's going to immediately break down to nitrogen monoxide. Oh, I'm sorry, NH to a weak base, I'm sorry, to ammonia, which is a gas plus H2O. Those are all in that little section I showed you in your green sheet and written a lot nicer than what I wrote it. And it's going to be something that you're really going to have to use, because if not, it kind of messes you up on a lot of different reactions that we use. All right. Questions, comments? I will tell you that as far as when we get started, a lot of people do struggle with this unit with writing the reactions, and that's usually because they don't know the solubility rules. That can definitely cause trouble. All right. So let's look at some of these examples. I have potassium nitrate and barium chloride, and I'm doing a double replacement reaction. So that means I end up having potassium chloride, and I end up having barium nitrate. This would be an easy one, because this has a group 1 metal. So group 1 metals are always aqueous, are always going to form ions. This has a nitrate. Those are always aqueous. So I have 2 AQs. So that would be an example of an NR. No reaction. As soon as you have 2 AQs, nothing's going to react. They're just going to stay as ions, and then you don't have to do all the rest of your work. All right, next one, sodium sulfate and lead nitrate. I kind of, whenever I see that lead, I kind of think about it, because I remember that a lot of times lead may make something insoluble. So once again, my 2 metals are going to exchange places. Sodium nitrate is what I form. Both of those are always soluble, so I'm going to immediately put AQ behind those. And then I end up getting lead sulfate. So lead sulfate is not one of the really easy ones. But because I have that heavy lead in there, it's going to be the solid. It's going to form your solid. And like I said, from using your solubility rules until you get used to the ones that are pretty straightforward, that's what you're going to need for that. So that would be a good reaction. I think I would need to do some balancing. I think I just need the 2 here. This is where we start off when we're writing net ionic equations, because you got to go through this part to finish. All right, next one, my iron and potassium are going to exchange places. So once again, I end up with that potassium. So I know that's AQ. And then I end up with iron hydroxide. So hydroxide are bases. We said the strong bases are soluble, and iron's not anywhere in group 1 or group 2. So this is going to be my solid. That's what my precipitate would be. And I think I would need to do a little bit of balancing what here. And I think I would need to straight over here. All right, so that comes all from, I think that's a good place to start. Let's see what we got here. All right, that's a good place to stop. Let's stop there. I do have a video I have to